Hello everyone. So welcome to this class of computer architecture. Good evening everyone. So before starting the today's class, I will discuss 2-3 questions which students sent me. आप लोगों के कुछ क्वेश्चंस थे, 2 या 3 क्वेश्चंस पहले मैं उनको एक्सप्लेन करूँगा, उसके बाद में वी विल स्टार्ट द प्रीवियस ईयर क्वेश्चंस ऑफ कंप्यूटर आर्किटेक्चर. ओके, so those questions which you have asked, so one of the questions is this. ओके, एक क्वेश्चन ये है जो आप लोगों ने पूछा है और ये क्वेश्चन थोड़ा सा ट्रिकी क्वेश्चन है. सो दिस इज अ लिटिल बिट ट्रिकी क्वेश्चन एंड दिस इज द कॉम्बिनेशन ऑफ 2 concepts and those concept are actually this is a single question on the virtual memory. Okay, this question is from virtual memory and we know that virtual memory is the part of disk. So virtual memory and disk, by combining these two things we have this question. Okay, so let me explain you what is this question, and before explaining this question let me explain what is the concept behind this question. Okay, we all know what is the concept behind this question, but we are not able to just combine the concepts, right? We are not able to combine the concepts. We all know what is the concept here. Okay, what concept they are using. Okay, let me explain you with a diagram what this concept is saying and what this question is all about. Okay, so we know that in the virtual page system, in the virtual memory system, CPU will generate a virtual address, right? CPU generates a virtual address which is divided into page number and offset, right? You will take this page number and you will go to the page table. Okay, number of entries in the page table will be equal to number of pages. If you have 4 pages, there will be 4 page table entries in this page table. So in this page table we will store the frame number. Okay, for example, page number 0 is in the frame number, let us say 3. Page number 1 is not in the memory. Page number 2 is in the frame number 1, let us say page number 3 is in the frame number, let us assume 0, right? Then we have valid invalid bit with every page number. Okay, with every page we have a valid invalid bit. For example, if a page is in the memory, then it is having the valid bit. If it is not in the memory, it will be I bit. So valid or invalid bit. Any page which is not in the memory, because page number 1 is not in the memory, so this means that it is a invalid bit. Invalid bit means the page is not found in the memory. So we know that if the page is not found in the memory, then it will be in the virtual memory, or you can say it will be on the disk. We have to load this page from the virtual memory to main memory, right? So if you find let us say we have generated a page number 2 and let us say some byte number 4. Okay, so we will take the page number 2 entry into the page table and we will take the frame number. Okay, so it will convert into the physical address. Now we will have a physical address like this. Okay, offset will remain same, the page number will be converted to the frame number. Now you will take this physical address. Okay, you will take this physical address and you will go to the main memory. Okay, let us say in main memory we have, okay, in main memory let us say we have 8 frames. We all know that main memory is divided into the frames, right? Main memory is divided into the frames. So this is frame number 0, 1, 2, 3, right? 4, 5, 6, 7. There are 8 frames in the main memory, right? So what we will do is we will search this address into the main memory. If it is found in the memory, data will be accessed from the memory, right? If the data is found in the memory, it will be accessed from the main memory. This concept is similar to the concept of the cache memory. So we have studied cache memory in the previous class. What we do is first we will search the data into the cache memory. If data is found in the cache memory, it will be sent to the CPU. If the data is not found in the cache memory, then we will search the data into the main memory, right? If the data is found in the main memory, then we will take the frame from the memory. Okay, we'll take that block from the memory and we'll transfer that block from main memory to from main memory to cache memory, right? So like that here, if the data is not found in the main memory, it is called as page fault, right? If the data is not found in the main memory, it is called as page fault. In case of page fault, you will go to the virtual memory, and virtual memory is the part of disk. Let us say we have a disk like this. Okay, we have a hard disk. So we have a hard disk, and in this hard disk let us say we have 16 we have a virtual memory in this hard disk. Okay, in this disk we have a virtual memory, and in the virtual memory, let us say we know that virtual memory is divided into the pages, right? In the virtual memory, let us say we have 16 pages like this. Okay, let us say we have 16 pages in this virtual memory. So initially all the pages will be in the so 14, 15 like this. We have, let us say, 16 pages into the virtual memory. Okay, this is your virtual memory which resides inside the disk. We know that, so CPU will search the data into the main memory. If the data is found in the main memory, then it will be sent to the CPU. But if the data is not found in the main memory, then data will be searched into the cache, into the virtual memory, that is the disk, right? So if the data is not found in the disk, it will be transferred to the main memory. Am I right? अगर आप सबको याद हो, we have talked about, just simply compare this concept with the concept we have studied in the previous class. Okay, in the previous class we have studied about the cache memory and the main memory. We say that CPU will generate an address and we will search this address into the cache memory, right? First we will search into the cache memory. If the data is found in the cache memory, it will be sent to CPU. But if the data is not found in the cache memory, then data will be searched into the main memory, right? The data will be searched into the main memory. So if the data is found in the main memory, it will be transferred to cache memory, right? When you will transfer the data from main memory to cache memory, you will require a block. Okay, because you are bringing one block from main memory to cache memory, you will search a free block into the cache memory. If it is direct map cache, then you will transfer the main memory block into the main memory block number mode, number of blocks into the cache memory. If it is associative cache, then you will transfer anywhere. If let us say cache memory is completely full, okay, you have to replace one of the blocks. Then at the time of replacement, you will see that if the replaced block is modified or not modified. Now this is story part 1. Then we have the story part 2. Story part 2 starts from the main memory. After main memory, we have a disk. Okay, after main memory, we have a disk. If the data is not found in the cache, it is called as miss. If the data is not found in the memory, it is called as page fault. Okay, in case of page fault, you will search the data into the disk. If data is found in the disk, you will transfer this block into the main memory, or you can say you will transfer the page into the main memory. This is what we talk about into the operating system. Okay, ये सब चीज़ें हम ऑपरेटिंग सिस्टम में बात करते हैं, और कल जो हमने बात करी थी वो कंप्यूटर आर्किटेक्चर में बात करी थी. अब जो मैं आपको कहानी बता रहा हूँ, व्हाट स्टोरी आई एम टेलिंग यू, दिस स्टोरी इज एक्चुअली स्टोरी पार्ट 2. Okay, this is the story part 2. Story part 1 you are studying into the cache, into the computer architecture. Right, now we are talking about main memory and disk. So I told you that if the data is not found in the main memory, then you will search the data into the disk or into the virtual memory, right? So let us say this main memory is completely full. This main memory is full and there is some data in every frame. In every frame we have some data. Okay, main memory is completely full. Now your, let us say, CPU want to access a data that is I. Okay, data I is in the page number. Let us say we have A here, B here, C here, D, E, F, G, H, I, J, K, L. We have the data like this. Okay, if let us say CPU want to search the data I, so data I is not in the main memory, so it will go into the virtual memory and will take the data I and then will transfer this data into the main memory. When CPU will bring this data, when operating system will bring this data from virtual memory to main memory, then operating system will search a free block. Okay, because to put this data, अगर आपको ये I data main memory के अंदर रखना है तो आपको एक free frame चाहिए होगा, but यहाँ पर free frame नहीं है, right? All the frames are occupied. Then what you will do is you will use the replacement algorithm. आपने पढ़ा होगा in virtual memory you have studied the page replacement algorithm. Okay, page replacement algorithm is used. There can be optimal algorithm, it can be LRU algorithm, it can be FIFO algorithm. If it is a FIFO algorithm, then you will replace I with A. But before replacing A, okay, before directly replacing A, you have to see whether A is modified or not, because we have the two copies of A. Okay, if let us say you have decided to replace I with A, okay, if you have decided to replace I with A, right, there are two options. What are the two options? Either A is modified or A is not modified, because after coming into the main memory, it is possible that CPU modified this data. If the CPU did modified this data, then we have two copies of A, one in main memory and one in virtual memory, right? If the data is modified, you have to send the update to virtual memory first, right? You have to send the updated data of A into the virtual memory, then only you can replace. अगर आपने डायरेक्टली रिप्लेस कर दिया तो ए के अंदर जो मॉडिफिकेशन हुआ था वो मॉडिफिकेशन फाइनली डिस्क के अंदर नहीं पहुंच पाएगा, right? If the page is modified, then you cannot directly replace. Okay, you cannot simply replace, but first you have to copy this data into the disk, right? If the page is not replaced, then you can directly, if the page is not modified, then you can directly replace. There's no problem because we have the same data in main memory and same data into the virtual memory, right? So according to the possibility, if the page is modified after coming to the memory or not, you have to decide whether we have to copy this data into the virtual memory or not. Okay, so to check whether this particular page is modified after coming into the memory or not, we have a bit called as modified bit. Okay, we have a bit called as modified bit. With every page in the page table, we will keep a bit, and that bit is called as modified bit. Okay, modified bit. This is valid invalid bit. Modified bit will tell you that whether this particular page is whether this particular page is modified by the CPU or not after coming into the main memory. Same thing you will study into the cache memory. Okay, same thing you will study. This is sometimes called as dirty bit also. This is called as modified bit or dirty bit. Okay, so you can call this dirty bit also. So if the dirty bit is set for a particular page, this means that this page is modified after coming into the main memory. The same concept you will study into the cache memory also. You must have heard about the cache coherence. Okay, आपने cache coherence के बारे में सुना होगा. अगर let us say कोई data, if you are bringing, let us say you have a cache memory. Okay, you have a cache memory in which you have 4 blocks, and you have a main memory in which you have, let us say, 8 blocks. Okay, you have a main memory in which you have 8 blocks like this. So block number 0, 1, 2, 3, 4, 5, 6, 7, and you have 4 blocks here, right? So it is possible that, let us say, you all know that data in cache memory will always come from the main memory, right? Data will come into the cache memory always from the main memory. Let us say you have some data here, A, B, C, D, E, F, G, H, right? CPU will modify the data into the cache memory only. CPU will access the cache memory directly. CPU will modify the data into the cache memory only. Let us say in cache memory you have A, B, C, D, this data, right? Now let us say CPU want to access the block number E. Okay, CPU want to access this block. Now this block E is not in the cache memory. You will go to the main memory and you will take this block and you will transfer it into the cache memory. But cache memory is full. Okay, if the cache memory is full and the cache memory is, let us say, set associative cache or associative cache, you will use the replacement policy. You will replace one of the blocks. But before replacing one of the blocks, you have to see whether this particular block after coming into the cache memory is modified or not. If this block is modified after coming into the cache memory, let us say this becomes A dash. Okay, this becomes A dash after modification. So you have to send the updation to the main memory first. Okay, you have to send the updation to the main memory first before replacing it. अगर ये मॉडिफाई नहीं हुआ तो फिर तो आप डायरेक्टली रिप्लेस कर सकते हो, राइट? अगर ये लेट अस से ए मॉडिफाई नहीं हुआ है कैश मेमोरी में आने के बाद, फिर तो कोई फ़र्क नहीं पड़ता, आप इसको डायरेक्टली रिप्लेस कर सकते हो क्योंकि सेम डेटा कैश मेमोरी के अंदर है, सेम डेटा मेन मेमोरी के अंदर है, कोई अपडेट प्रॉब्लम नहीं होगी. So this is called as cache coherence problem if we have different copy in main memory and different copy in the cache memory, right? For that, for updating into the main memory, we use two techniques that is called as write through and write back. Same thing is here. When you are replacing any page into the main memory, then you have to check whether this particular page is modified or not. If it is modified, then you have to send the update to hard disk first and then you can replace it. Okay, you cannot, if let us say if the data is not modified, then you can directly replace it. Okay, now let us try to understand the question. Okay, the question is saying that we have a paged system supports a paged virtual memory using a central processor with a cycle time of 1 millisecond. Okay, so one cycle time is given. One cycle time is 1 microsecond. 1 microsecond. Okay, it costs an additional 1 microsecond to access a page other than the current page. Okay, if you are accessing any page, then the current page, then it will take one more additional microsecond. right? Page have 1000 words, that means page size is given, the page size is 1000 words. Okay, and the paging device is a drum. You can say drum is like a disk. Okay, you have a disk, so you have a disk and the rotation speed of disk is given. Okay, rotation speed is given, that is 3000 revolutions per minute, that is 3000 rpm. Okay, rotation speed is given. From here you will find out the rotational latency. अगर आप सबको याद हो rotational latency कैसे find out करते हैं, you will find out the rotational latency, right? And the transfer speed is, it transfers 1 million words per second. Okay, it transfers 1 million words per second. Okay, so you have to simply the transfer rate is, okay, the transfer rate is 1 million words per second. Further, 1% of all instructions executed accessed a page other than the current page. Okay, 1% ऐसे थे. Okay, you have 1% pages which access than the current page. That means we have 99% pages. Okay, we have 99% instructions which are actually accessing the current page only. Okay, 99% instructions are using current page only. Only 1%, okay, only 1% of all instruction executed accessed a page other than the current page, If you are accessing only current page, then you will require only one cycle. Okay, you will require only one cycle, that is only 1 microsecond. Now see second possibility. Second possibility is very big. Second possibility says that 1% means 0.01. 1% pages, 1% instructions accessed another pages than the current page. Okay, now the instruction that accessed another page, 80% accessed. Okay, 80% accessed. Okay, 80% of the 1% accessed a page already in the memory. Okay, if the page is already in the memory, then it will take only 2 cycles. Okay, 2 cycle. Why? Because it is saying that it costs an additional 1 microsecond to access a page other than the current page. Okay, so these are the pages which are this is the possibility in which you are accessing other page than the current page. Okay, in that case 80% of the pages will require 2 microseconds. Okay, 2 microseconds. So 80% accessed a page already in memory. When a new page was required, okay, that means we have, so 80% accessed a page which is already in memory. So 20% are not in memory. So if the 20% are not in memory, then you have to bring those pages from the hard disk. Okay, you have to bring those pages from the hard disk. So it is saying that the replaced page was modified 50%. Agar, let us say, if the page is not in the memory, then you have to go to disk. You will bring a page, right? When you are bringing a page, when you are placing a page into the memory, there are 2 possibilities. If the replaced page is modified, then you have to first copy into the hard disk. If it is not modified, then you can simply replace it, right? So out of these 50%, okay, we have the 50% pages. Okay, the replaced page was modified 50%. If it is modified, then first you have to copy. Okay, you have to go to the disk and you have to copy that page from memory to disk, and then you will access that particular page from the disk. Okay, that means there will be 2 times disk access. Why? First time to save this page from memory to disk because it is modified, and then second time to access the required page from the disk, right? And the disk access require, so to transfer one page from disk to main memory or main memory to disk, okay, to transfer one page from disk to main memory or main memory to disk, it will require how much time? See, what is the transfer time? Okay, what is the transfer time to transfer a page from main memory to disk? So we have 1000 words. Okay, 1000 words. Okay, one page size is 1000 words, and the disk transfer rate is 1 million words per second. So 1 million words means 1 million words per second, or you can say transfer time is nothing but, so it will be, so 3030 gone, so it will be around 10 to the power minus 3 seconds. Okay, 10 to the power minus 3 seconds, right? 10 to the power minus 3 seconds, or you can say transfer time will be 10 to the power minus 3. I can write it, if I want to convert this into the microsecond, it will become 10 to the power 3, that is 1000 microseconds. Okay, that means transfer time will be 1000 microseconds. If I want to convert this into the microsecond, I will multiply by 10 to the power 6. Okay, this will become 1000 microseconds. So transfer time will be 1000 microsecond. Then we are given the rotational latency. अगर आप सबको फॉर्मूला याद हो, okay, अगर सबको फॉर्मूला याद हो, total time taken is rotational latency plus transfer time, okay, plus seek time plus transfer time, right, plus other if anything is given. So we know that we are given only two times, transfer time and the rotational latency. We can find out the rotational latency from here. Okay, we have 3000 rotations per minute, 3000 rotations in 1 minute. We can say one rotation will be in 60 into 10 to the power 6 divided by 3000 microseconds. Okay, this will be one rotation time. So we can see I have converted 1 minute into the microseconds. Okay, so I will convert this into seconds, multiply by 60, then microsecond multiply by 10 to the power 6. Okay, so one rotation time will come out to be 20,000 microseconds. And we know that rotational latency is nothing but half of the one rotation time, right? Half of the one rotation time. So one rotation time is 20,000. So rotational latency will be 10,000 microseconds. Okay, 10,000 microseconds. Am I right? So so disk access time will become 10,000 microseconds. Okay, 10,000 microseconds plus 1,000 microsecond, that is simply your transfer rate. Okay, that is transfer time. Transfer time plus rotational latency will be the disk access time. So 50% of the time you will simply replace the page, plus 50% of the time, okay, that is 0.50 plus 50% of the time you will have to access the memory disk two times. Okay, because you have to copy the modified page into the main memory into the disk. So this will become double, that means 20,000 plus 2,000, because you have to access the disk two times microseconds. Okay, so you will solve this complete equation. You will get this will become so we have the equation like this now. Okay, so equation is like this now. We know that transfer time we have find out. Okay, transfer time is nothing but size of data you want to transfer. So we have to transfer one page, right? One page transfer time will be transfer size of the page divided by bandwidth, right? Bandwidth is given in the question, that is 1 million words per second. So page size is 1000 words and the bandwidth is 1 million, that is 10 to the power 6 words per second. Okay, words per second. So this will become 10 to the power minus 3 seconds, right? I can convert this into the microseconds and I can multiply by 10 to the power 6. This will become 1000 microseconds, right? Then I told you that we can find out the rotational latency, and rotational latency is nothing but half of the one rotation time, right? So one rotation time we can find out from the rotation speed given, that is 3000 rotations per minute. Okay, in 1 minute is rotating 3000 times. Then I can say one rotation time will be 1 by 3000 minutes. I can convert the minute into the seconds. This will become 60 into 10 to the power 6 microseconds. Okay, this will come out to be 20,000 microseconds, right? 20,000 microseconds, sorry, 20,000 milliseconds. So this will come 20. Okay, so 20,000, and then these three zeros will divide these three zeros. Okay, so this will become 20,000 milliseconds. Okay, 20,000 milliseconds. I can convert this into the microsecond and this will become 20 microseconds. Okay, this will become 20 microseconds. Then so this is your rotational latency, and the rotational latency will come out to be 1 by 2. Okay, 1 by 2 into one rotation time, that is 20. Okay, this will come out to be 10 microseconds. Okay, 10 microsecond will be your rotational latency, right? So this will be one page 10 to the power 6 words per second. Okay, it is given. Transfer rate is 1 million words per second. Okay, 10 to the power 6 words per second. So this will become one page is equals to 1000 words, 20,000 microseconds. So 60 into 10 to the power 6 divided by 3000, 20,000 microseconds. Yes, it will be 20,000 microseconds. Okay, 20,000 microseconds it will be. Okay, yes, it will be 20,000 microseconds, and 10,000 microseconds will be rotational latency. So we know that equation is 0.99 into 1 cycle, that is into 1 microsecond, plus 0.01%, and out of those 80% will access the current page, and that is already in the memory. That means it will require 2 microseconds only, 2 cycles only, plus 20%, that is 20% of the 1% will require, 50% will be modified. Okay, 50% are modified, that means 10,000 plus 1000. Okay, plus 50% will require memory access 2 times, that is 20,000 plus 2000. Okay, you will solve this equation and you will get 34 microseconds, around 34 microseconds. Okay, main thing is if you can understand the concept, then you will simply solve the question. This is the case when you are accessing the current page only. When you are accessing the current page, when you are accessing the other than the current page, then the page may be in the memory or it may be on the disk. If the current page is in the memory, then this is the time. If the current page is not in the memory, then there are two cases. Either the replaced page is modified or it may not be modified, right? So 34.006 will be approximately equal to 34. Okay, I also got 34.006. So the answer will be 34. Right. So this is the question, and I think someone asked one more question. किसी और का एक क्वेश्चन और था कि एक डिस्क है. Okay, we have a disk on which we have a disk on which we have a sector. On one sector we have 63 we have a surface on which we have a, okay, the capacity of one track is, okay, in this question it is given that one track is having. So if this question comes in the examination, I am sure that only few people will be able to solve this question. ये क्वेश्चन थोड़ा सा ये हो सकता है कि ये बोल सकता हूँ कि ये डिसाइडिंग फैक्टर हो सकता है. अगर इस क्वेश्चन को लेट अस से 50,000 पीपल्स में से अगर 10 लोगों ने भी कर दिया तो वो टॉप पे पहुँच जाएंगे. So this question, like as I told you that complex questions are the decision makers, right? They will actually, yeah, this was the net previous year question. This question was asked in the August 2016. This question was asked in the August 2016 paper 3. Question number 51. Okay, question number 51 of the paper 3 of August 2016. So someone asked a question that we have a track on which we have 63 sectors. Okay, and so we have a track on which we have 63 sectors, and this we have a, so in first track is on the location 000, and the second so first sector, this is the address of the 0th sector. Okay, this is the address of the 0th sector, and this is the address of the first sector. Okay, this is the address of the first sector, right? So this address format is like this. The first, this represent the cylinder number. Okay, this represent the surface number, and this represents the sector number. Okay, so we have to find out the address format in this scenario, that is cylinder number, surface number, and the sector number for the sector 1039. Okay, we are given a sector that is 1039. We have to find out the address format, that is on which cylinder it will be, on which surface it will be, on what is the sector number, right? So we know that we have a disk like this. The disk is arranged in this form. So we have a spindle like this. Okay, we have a spindle like this, and on this spindle we have the platers. Okay, we have the platers. On the plater we may have one surface, or we may have two surfaces, right? Let us say these are the tracks. Okay, these are the tracks on the surface. So we have these tracks. What is the meaning of cylinder? Cylinder is nothing but, so first cylinder is called as, after joining first track of every disk, Okay, first track of every surface is called as first cylinder, and second surface, okay, you can say second surface, second track of every surface is called as second cylinder, and this will be third cylinder. Okay, so number of cylinder in a disk will be equal to number of tracks. Okay, because we are taking one track of each surface, and we are calling it one cylinder. Okay, we are calling it one cylinder. So it is given in the question that we have a disk, okay, on which we have two-sided recording. Okay, two-sided recording means that we can record on both of the sides. We can record in the upside also, in the downside also, right? So we have a one track in which we have 63 sectors. We have to find out the surface number, cylinder number, and the sector number for this particular sector. Okay, sector 1039. So you know that on one track, okay, on this particular track you will have how many sectors? You will have 0 to 62 sectors. Okay, sector number 0 to sector number 62 you will have on this surface, okay, on this track, on the upper surface, and on the down surface also you will have 63 to you can say 125. Okay, because every track is having 62 sectors, so you will have 62 sectors on the upside and on the downside also. Then you will go to the second, you will go to the first track of the second cylinder. Okay, first track of the second cylinder. On this cylinder you will see that, so on the same cylinder we are going, on the same cylinder we are there. On the cylinder number 0 we have this track, then we have this track, we have this track, right? So then we will have on the cylinder number 0, then we will have cylinder number next sector will be from 126 to, you can say, something 9 plus 6 to 8, 189. Then you will have 192, something like, you can say 250. Okay, so we know that on one particular sector, on one particular surface, if you talk about one surface, upside and downside, you have total 126, or you have total 126 sectors, right? 63 on the upper side and 63 on the downside. So sector number 0 to 125 will be on the one surface, then 126 to 250 will be on the second surface. So there are two surfaces. Okay, there are two surfaces on this platter. We have upper surface and down surface, then two surface here, right? Then you will have 251 to, you can say, 375, right? Then 376 to 500. Okay, this will be so this will be two surfaces, this will be two surfaces, right? Then you will have like this 501, so 376 to 500, then 501 to plus 125 will be 625, then 626 to, you can say, 750. Okay, this will be two surfaces, this will be two surfaces. Sector number, these are the sector numbers. Then sector number 751 to 875 will be on the next surface. Then 876 to you can say 1000 will be on one other surface, right? So we have surface number 1 2 3 4 5 6 7 8, that is surface number 16, right? Right now we are on the surface number 16. Right now we are on the surface number 16. Okay, and cylinder number is 0. We are on the same cylinder, right? We are on the same cylinder. Cylinder number is 0, surface number is 16. Okay, after reaching the surface number 16, then you will read all these sectors. Okay, you will store the sectors, 39 sectors, right? 39 sectors will be stored here. So from this you can find out the sector number next. So we have three options. Now I think you can solve this question, right? I think now you can solve this question. So sector numbers are actually numbered from 0 to 63 on one particular surface, then 0 to 62, then 63 to 125 on the on the down surface. So on one particular platter, on one track you have 126, you can say you have total 126 sectors, because it is two surfaces, two sided, right? So before starting the previous year question, let me solve one more question which I skipped in the previous class. So we skipped this question in the previous session when we are discussing about. Yes, Kushba, I will discuss about that. Okay, so we have this question from GATE 2018. Okay, yes, ये question मैंने skip किया था, तो इस question को अभी solve करते हैं. This is saying that we have a 16 integer registers R0 to R15. We have 64 floating point registers F0 to F63. It uses a 2-byte instruction format. It is saying that we have a instruction size of 2 byte. 2 byte means 16 bits. Okay, we have a instruction of 16 bits. And we have 4 kind of instructions. Okay, there are 4 categories of instruction: type 1 instruction, type 2, type 3 and type 4. Okay, type 1 category consists of 4 instructions. Okay, there are 4 instructions of type 1 category, each of which with the 3 integer registers. Okay, we have to specify 3 integer registers. Okay, so integer register something here, integer register, so there will be 3 integer registers. So to specify one of the 16 integer registers, we will require 4 bits. Okay, 4 bits will be required to represent the 16 registers, right? So this opcode field will also be of 4 bits. There are 2 ways of solving this question. The first way is this, and second way is I will tell you. This is the type 1 instruction. Okay, you have type 1 instruction in which you have 3 integer registers. Okay, then you have type 2 instructions, and in the type 2 instruction, okay, in the type 2 category consists of 8 instructions, each with 2 floating point registers. Okay, 2 floating point registers, floating point register 0, floating point register 1. Okay, so we have 64 floating point registers. To specify one of the 64 floating point registers, you will require 6 bits, and instruction is of 16 bits. 6 plus 6 is 12. That means opcode will be of 4 bits, right? Opcode will be 4 bits. This is called as type 2 instruction. Okay, this is your type 2 instruction. Then you have type 3 instruction, and the type 3 instruction is like this. In the type 3 instruction, we have 14 instructions. Okay, each with 1 integer register. Okay, each with 1 register operand and 1 floating point operand. Okay, we have 1 floating point and 1 register. So to specify one of the floating point registers, you will require 6 bits, and to represent one of the integer registers, you will require 4 bits, because you have 16 integer registers and 64 floating point registers. So you will have 4 bits. You will have 6 bits for the opcode part. Okay, you will have 6 bits for the opcode part. So these are the type 3, type 1, type 2 and type 3 instruction formats. Okay, then you have type 4 category, and it is saying that type 4 category consists of n instructions, each with a floating point register operand. Okay, you have n instructions with 1 integer, so we have only floating point integer there. Okay, floating point register operand. So floating point register operand will require 6 bit to represent out of the 64. So opcode in this will be of 64 bits. Opcode will be of 10 bits in this. Okay, opcode will be of 10 bits, right? And this is the address part of 6 bits. You can solve this question in 2 ways. The first way is your expanding opcode technique. या तो आप इस क्वेश्चन को expanding opcode technique से भी कर सकते हो. ओके, इसको आप इस तरह से मान लो कि ये आपका 3 एड्रेस इंस्ट्रक्शन है, ये 2 एड्रेस इंस्ट्रक्शन है, ये भी 2 एड्रेस इंस्ट्रक्शन है, और ये 1 एड्रेस इंस्ट्रक्शन है. तो आपको बताना है कि नंबर ऑफ 1 एड्रेस इंस्ट्रक्शन कितने होंगे. ओके, आपको n की वैल्यू बतानी है. आपको बताना है कि नंबर ऑफ 1 एड्रेस इंस्ट्रक्शन कितने होंगे. आपको इस तरह से भी देख सकते हो इस क्वेश्चन को. या फिर दूसरा बहुत ही सिंपल सा मेथड है. Okay, and that method can be applied to expanding opcode technique also. From this method you can solve the question of expanding opcode technique also, right? Then the technique is that it is saying that we have a 16-bit instruction. Okay, you have a 16-bit instruction. If you have a 16-bit instruction, then total number of combination possible are how many? Okay, total how many instructions are possible? Total 2 to the power 16 instructions are possible, right? Total 2 to the power 16 instructions are possible, and out of these 2 to the power 16 instructions, some can be 2 address, some can be 3 address, some can be 1 address. So it is given in the question that we have 4 instructions. Okay, we have 4 instructions which uses 3 register operands. Okay, 4 instruction will use 3 register operands. That means 4 into 2 to the power 4 into 2 to the power 4 into 2 to the power 4. Okay, these are the first category. Okay, this is the first category in which you have 4 instructions and every instruction will use one of the integer registers, right? One of the integer registers, you have 16 integer registers, right? Then we have the second category, right? We have the second category, that is that will use type 2 category, consists of 8 instructions, each with 2 floating point registers. Okay, so this is the format of type 2 category. So type 2 category is having 8 instructions, okay, each with the 2 floating point operands, right? 2 floating point operands, because the address part is of 6 bits, that means 2 to the power 6 floating point operands are possible, right? Plus then you have type 3 instructions, and type 3 instructions are, so type 3 consists of 14 instructions, each with one integer operand, each with one integer register, okay, one integer register and one floating register. So we have 14 category 3 instructions, with every instruction having 2 to the power 4 into 2 to the power 6, okay, 2 to the power 4 register operands, 2 to the power 6 floating point operands. Then you have n instructions of type 4 category, okay, you have n instruction of type 4 category, in which you will use only one floating point operand, okay, you will use only one floating point operand, that is n into 2 to the power 6, right? So you can solve this equation with for the value of n. All these combinations which should be equal to 2 to the power 16, because 2 to the power 16 combinations are possible. You can make any number of 0 address, 1 address, 2 address, 3 address instructions, but combining all those instructions, they should be equal to 2 to the power 16, right? So this is 2 to the power 16 equals to, this will become 2 to the power 2, 2 to the power 4, 2 to the power 4, that is 2 to the power 10, plus this will become 2 to the power 9 into 2 to the power 6, that is 2 to the power 15. This will become 2 to the power 15, plus this will become 2 to the power 10, 14 into 2 to the power 10, and this is n into 2 to the power 6, right? So we can solve this equation now for the value of n. Okay, so what we can do is, we can take the common from here. We can say 2 to the power 16 minus 2 to the power 10 minus 2 to the power 15, okay, minus 14 into 2 to the power 10 equals to n into 2 to the power 6. Okay, this will become, we can take the common 2 to the power 10 here, okay, this will become 2 to the power 6 minus 1 minus 2 to the power 5, okay, minus 14 equals to n into 2 to the power 6, right? And this will come out to be 2 to the power 14, 6 plus 6 12 plus 3 15, 2 to the power 14 कहाँ पर आएगा, 6 plus 4 10, 6 plus 6 12, 12 plus 3 is 15, yeah, this will be 2 to the power 14, okay, this will be 2 to the power 14, मैंने एक 2 to the power 4 नहीं देखा. So this will be 2 to the power 14, 2 to the power 15, so this will come out to be 2 to the power 4. Okay, so this will become 2 to the power 10 into 64 minus 16 minus 32 minus 14 equals to n into 2 to the power 6. Okay, so this will become 16 minus 16 minus 14 is 30, 32 is 30, and 32 is 60, 30, 16 plus 14 is 30, and 32 is 62, 64 minus 62 is 2, that means 2 to the power 10 into 2 equals to n into 2 to the power 6. So from here the value of n will become equals to 2 to the power 11 divided by 2 to the power 6, okay, that will come out to be 2 to the power 5, that is equals to 32. Okay, so there will be total 32 instructions of this format, right? So let's see, अगर हम ये can we apply this technique for the expanding opcode technique. So I told you the questions of expanding opcode technique can be solved like this. Okay, I told you a technique. Okay, now I will tell you one other technique to solve the questions of expanding opcode technique. Okay, so this question is saying that you have a one word long instruction, one word is size of 32 bits. Okay, we have a one word long instruction that is of 32 bits. Okay, it has 64 registers, each of which is 32 bit long. It supports 45 instructions. It needs to support 45 instructions which have an immediate operand in addition to two register operands. Assume that the immediate operand is n, so this question is not for expanding opcode technique. This question we can see. Okay, so this question is having a 11-bit instruction. Okay, we have a 11-bit instruction. So this means that we can have total number of instructions possible is total number of instructions can be 2 to the power 11. Remember, I am saying total number of instructions. I am not saying total number of operations. Total number of operation and instruction are different thing. That when we are talking about operations are we are talking about opcode part only. Okay, so total you have 2 to the power 11 instructions, out of which so address field is of 4 bits, right? The computer uses expanding opcode technique. It has 5 to address instructions. 5 to address means 5 instructions will use 2 addresses. Okay, so address format is of 4 bits, so it will be like this: opcode address 1 address 2. Okay, so address part is of 4 bits, so it will be like 5 into 2 to the power 4, 2 to the power 4. Okay, we can use the combinations of address 1 and address 2. Okay, the combination of address 1 can be 2 to the power 4 and 2 to the power 4 for address 2. Plus it is saying that we have 32 one address instructions. We have 32. In the 32 instructions, we will have one address. One address means 2 to the power 4 addresses are possible, right? We have to find out number of zero address instructions. Let's assume that number of zero address instructions are n. Okay, number of zero address instructions are n. So we have to find out the value of n. The value of n will be 2 to the power 11 minus 5 into 2 to the power 8. Okay, minus 2 to the power 9, right, equals to n. So the value of n will become, we can take the common 2 to the power 8 here. So 2 to the power 8 we will take common. This will become 2 to the power 3, that is 8, minus 5 minus 2 to the power 1. Okay, so the value of n will become 8 minus 5 minus 7. So 8 minus 7 will be 1. So this will become 2 to the power 8. So answer will come out to be 256. That is how also you can solve the questions of expanding opcode technique. एक टेक्निक मैंने आपको पहले बताई है, ये टेक्निक भी आप यूज़ कर सकते हो. ओके, यू कैन यूज़ दिस टेक्निक ऑल्सो. अंजलि अरोड़ा, आई हैव टॉट दिस कॉन्सेप्ट एटलीस्ट 1000 टाइम्स. इसलिए आप अभी भी गलत आंसर कर रहे हो. कम से कम 1000 बार इस टेक्निक को पढ़ा चुका हूँ मैं. अगर आप ऐसे भी करते हो, अगर आप इस क्वेश्चन को उस पुरानी टेक्निक से भी करते हो कि पहले आप फाइंड आउट करो नंबर ऑफ 2 एड्रेस इंस्ट्रक्शंस. ओके, नंबर ऑफ 2 एड्रेस. ओके, नंबर ऑफ 2 एड्रेस इंस्ट्रक्शन कितने होंगे? So 4 plus 4 8, and this field will be of 3 bits. Total number of 2 address instructions will be 8. Out of 8, how many you have used? You have used 5 2 address instructions. Okay, so you have used 5 2 address instructions. Remaining are, so remaining 2 address instructions are 3. Right, now number of one address will be remaining combination, that is 3 into 2 to the power address field, that is 4, that will be 48. Right, so now remaining one address is out of the 48 you have used 32, so remaining are 16. So number of zero address instructions will be remaining combination, that is 16 into address field, that is 2 to the power 4. This will be 2 to the power 8, that is 256. Again you will get the same value. Okay, so you can solve any questions of expanding opcode technique using this particular technique. Okay, this technique is useful when you have the form address field of different sizes. Let us say we have this address 1 field of 4 bits, this address 2 field of 8 bits. Then in this case this technique will be useful. This technique can be applied for the equal size address field and the unequal size address field also. Okay, so I think we have solved all the questions of addressing modes and instruction format. Let us solve one question of NTA NET also on this. Okay, we do not have anyone. ये जो नई टेक्निक है वो बहुत ईजी है, नई टेक्निक तो बहुत ईजी है, उसमें आपको कुछ करना ही नहीं है, बस आप 10 सेकंड में क्वेश्चन सॉल्व कर सकते हो। विद द न्यू टेक्निक यू डू नॉट नीड टू सी एनीथिंग, ओके, डायरेक्टली क्वेश्चन को सॉल्व करना है। ये वाली टेक्निक फास्ट है और बहुत ही ईजी है। जैसे कि ये क्वेश्चन था, इस क्वेश्चन को आप देखो कितना टाइम लगेगा सॉल्व करने में, जो क्वेश्चन हमने कल किया था। सो वी सॉल्व अ क्वेश्चन दैट वाज अ वेरी सिंपल क्वेश्चन। ओके, ये क्वेश्चन था, इसको देखो आप। तो इसको, इस टेक्निक को अगर आप अपने अपने इस टेक्निक के थ्रू करते हो तो आपको पता है कि इंस्ट्रक्शन का जो साइज़ है, इंस्ट्रक्शन का साइज़ 16 बिट है। ओके, यू हैव इंस्ट्रक्शन साइज ऑफ 16 बिट्स। सो टोटल इंस्ट्रक्शन कितने होंगे, 2 to the power 16। Okay, out of the 2 to the power 16 instructions, we have 14 double address instruction, that is 14 into 2 to the power 6 into 2 to the power 6. Okay, double address. Then we have 127 single address, so 127 into 2 to the power 6, plus you have to find out how many zero address instructions will be there, no address or zero address instructions. So number of zero address instructions will be n equals to 2 to the power 16 minus 14 into 2 to the power 12 plus 127 into 2 to the power 6. Okay, from here you can take the common, n equals to, you can take the common 126, 2 to the power 6 you can take common from here. This will become 1024 minus 14 into 64. Okay, 14 into 64, and this will be minus 127. Okay, you will find out the value, you will get 64. So 14 into 64 will be 896 plus 127. 1023, 1024 minus 1023. This will be equals to n equals to 64 into 1, that is 64. इसमें आंसर गलत नहीं हो सकता, जैसे कि देविका बोल रही है कि इसमें क्वेश्चन, इसमें आंसर जो है वो गलत हो सकता है। बहुत ही सिंपल, इसमें डायरेक्ट, क्योंकि इक्वेशन आपको, आप इक्वेशन बनाओगे और इक्वेशन आप बिल्कुल सही ही सॉल्व करोगे, इक्वेशन में तो कोई गलत होने की चांसेस है ही नहीं, राइट। Yes, Paranita, from the computer architecture topic, they will ask most of the time they will ask the numericals only. Okay, they will ask mostly numericals. अरे 896 नहीं आएगा देविका जी, उसमें 127 भी तो ऐड करोगे, 127 ऐड नहीं करोगे। 896 और 127 ऐड करो, 1023 आएगा। Okay, so let us solve some questions on computer architecture and organization. तुमसे अगर अंजलि, अगर तुम्हारी मल्टीप्लिकेशन और एडिशन भी गलत हो रही है ना, फिर तुम कर ही क्या रहे हो? अगर तुम मल्टीप्लिकेशन और एडिशन में भी गलतियां कर रहे हो, फिर तुम कर ही क्या रहे हो? मतलब इतने दिनों से पूरा टाइम तुम पढ़ रहे हो, है ना, अच्छे अच्छे क्वेश्चंस कर रहे हो डेली, इतनी मेहनत कर रहे हो, और फिर तुम इतनी मेहनत करने के बाद भी मल्टीप्लिकेशन में गलती कर दे रहे हो, क्या फ़ायदा हो रहा है? आपके पास में बहुत कम टाइम है, मैं समझ रहा हूँ उस बात को, लेकिन आप कम टाइम होने का मतलब ये नहीं कि आप बस सब कुछ मगअप करते जाओ और प्रैक्टिस ढंग से करो ना, राइट। जल्दी ना करो, आप बहुत जल्दी कर रहे हो चीज़ों में, आप जल्दी कर रहे हो कि जल्दी जल्दी सब्जेक्ट कंप्लीट कर लूँ, जल्दी जल्दी रिवीजन कर लूँ, जल्दी जल्दी इसके न्यूमेरिकल्स कर लूँ। आप बहुत मेहनत कर रहे हो, लेकिन मेहनत सही डायरेक्शन में नहीं कर रहे हो, जिस तरह से मुझे दिख रहा है। आप अगर मतलब एक्सपेंडिंग अपवर्ड टेक्निक के क्वेश्चंस भी गलत कर रहे हो, फिर मैं क्या कहूँ उस बात में? अरे 896 ही लिखा है मैंने देविका, देविका मैंने 64 इंटू 14 896 ही करा है। 896 में फिर 127 भी तो ऐड करोगे ना, माइनस में 127 भी तो है, ये 1023 आएगा ना। सिक्सटी फोर इंटू 14 तो 896 ही आएगा, उसके बाद में 127 भी तो है। कुछ इक्वेशन कुछ इस तरह से है ना, 1024 माइनस 16 माइनस 64 इंटू 14 माइनस 127 भी तो है ना वहाँ पे, ये दोनों को ऐड भी तो करोगे ना आप। 896 है ना, दोनों माइनस के हैं, माइनस का 1023 आएगा, 1024 माइनस 1023 विल बी 1. Okay, so solve this question. A computer uses 1 gigabyte of memory. Okay, 1 gigabyte of main memory. Previous question का आंसर will be 64. मीना, previous question का आंसर will be 64. देविका, डोंट बी सॉरी, दैट्स फाइन. मुझे लगा कि आपको लग रहा है कि आपने शायद वो आप 127 ऐड करना भूल गए. दैट्स ऑल. So a computer uses 1 gigabyte of memory. Memory is byte addressable. How many address lines required to connect this memory with the computer? Okay, so if you have a main memory of 64 byte, you have a main memory of 1 gigabytes. Okay, so number of address lines, I told you that number of address bit will be equal to number of address bits will be equal to 2 to the log base 2 to the power 32 bytes, right? So number of address bits will be 32. Okay, there will be 32 address lines. Okay, so this is 1 gigabyte, so 2 to the power 30, that is C. Okay, let us say if the memory is word addressable. Okay, if memory is word addressable, नहीं खुशबू, आई एम नॉट एंग्री. ओके, सॉरी गाइस अगर मैं थोड़ा रूड हो रहा हूँ. आई डिडंट मीन इट. आई थिंक फ्लो में कुछ ज़्यादा ही हो गया. ओके, आई एम नॉट एंग्री. इफ मेमोरी इज एड्रेसेबल, लेट इज वर्ड एड्रेसेबल, एंड द साइज ऑफ द वर्ड इज, प्यारे बच्चों, इफ द साइज ऑफ द वर्ड इज 4 bytes. Okay, if the size of the word is 4 bytes, can you tell me number of address lines now? How many number of address lines will be there? If the memory is word addressable and the size of the word is 4 bytes. Okay, this kind of question is being asked in NTA NET. अरे तुम लोगों ने कुछ नहीं किया है, मैं पता नहीं. So in this case you have to find the number of words. Okay, you have to find out number of words. So number of words in this memory will be number of bytes. Okay, number of bytes are 2 to the power 30 bytes. Okay, number of bytes are 2 to the power 30, and the size of one word is 4 bytes, that is 2 to the power 2 bytes. So number of words in this memory will be 2 to the power 28. Okay, so now if you want to find out the number of addressing lines, then this will be log base 2 to the power 28, that is 28 bits. Okay, there will be 28 bits address, 28 bit address, or you can say 28 address lines, because one line can carry 1 bit of address. Okay, so next question is assume a CPU takes 17 cycles in worst case to execute an instruction. Number of cycles required to execute current instruction by CPU is 12. Okay, if an interrupt occurs while executing current instruction, then after how many cycles it will be recognized? Okay, it is saying that we have instruction. Okay, and to execute one instruction, this is a very logical question. To execute one instruction, it takes 17 cycles. Okay, it takes 17 cycles to execute an instruction. Number of cycles required to execute the current instruction by CPU is 12. In worst case it is in worst case. Sir, if 32 into 16 is given, then in this case 5 address lines and 16 data lines. Very good. Yeah, that is right. Because usually the memory format is given in like this. Memory format is given in this form. Let us say 1k, okay, 1k into 16. This means that number of cells in the memory. This is telling you the length of the memory, number of cells and the size of each cell. Okay, size of each cell, right? So number of cells you can find out, so you can find out the address lines from this. From the number of cells you can find out the address lines. So address lines will be log base to 1k, that is 10, and data lines will be 16. यस बहुत ही लड्डू क्वेश्चन है खुशबू. नीलीट में तो बहुत ही सिंपल से क्वेश्चन पूछते हैं, राइट. सो दिस इज सेइंग दैट नंबर ऑफ साइकिल्स रिक्वायर्ड टू एग्जीक्यूट द करंट इंस्ट्रक्शंस बाय सीपीयू इज 12. ओके, ये कह रहा है कि मतलब एक किसी सीपीयू के अंदर इन दिस सीपीयू, or in worst case it will require 17 cycles to execute any instruction, but the current instruction which we are executing is it will take only 12 cycles. If an interrupt occurs while executing the current instruction, if interrupt comes, okay, you are executing instruction in the CPU, the current instruction, okay, and any interrupt comes, okay, interrupt come to the CPU. So if an interrupt occurs while executing the current instruction, then how many cycles will it will be recognized? After how many cycles it will be recognized? So we know that यहाँ पे आपको सिंपल सा कॉन्सेप्ट यूज होगा. I told you that CPU will acknowledge the interrupt only after finishing the execution of the current instruction. Okay, and the execution of current instruction will complete after 12 cycles. That means CPU will acknowledge the interrupt after 12 cycles. Right, a simple concept which I told you, that if any interrupt comes to the CPU will acknowledge that interrupt only after finishing the execution of the current instruction, right? So the answer will be 12. Next question is, for executing indirect address instructions, the following machine cycles are performed. Okay, so as I told you in the previous class, in the control unit class also, if any instruction is using indirect addressing mode, then before fetching the operand, okay, we have to fetch the address. That means we have to run an indirect cycle, right? And this is the indirect cycle. You will transfer the address part of the instruction register into the MAR, then you will read the memory from this location and will transfer data into the MPR, and then from MPR address part to IR address part. So that is indirect cycle. If your instruction is using indirect addressing mode, then you will require an indirect cycle. Okay, next question is, a processor has average instruction execution time as 2 microseconds. Okay, it takes 1 microsecond. Okay, so it takes 2 microseconds. Okay, it takes 2 microseconds to execute one instruction. Then the MIPS rate of the processor is what? MIPS means million instruction per second. What is the MIPS rate? Okay, million instructions per second. How many million instructions it can execute per second, right? So we know that in 2 microseconds we can execute one instruction. Or I can say, if I convert this into the seconds, this will become 2 into 10 to the power minus 6 seconds. I am converting microsecond to the second. In 2 into 10 to the power minus 6 seconds, it can execute one instruction. Or you can say in 2 seconds, okay, in 2 seconds it can execute 10 to the power 6 instructions. 10 to the power 6 means 1 million instruction, right? 10 to the power minus 6 will go this side, this will come into the plus. So in 1 second it can execute 1 by 2 into 10 to the power 6 instructions. That means 500,000 instruction. It can execute 500,000 instructions in 1 second. 500,000 instructions. That means MIPS rate is half. MIPS is 0.5 million instructions per second. Okay, it can execute 0.5 million instructions per second. This is a simple aptitude question. इनडायरेक्ट एड्रेसिंग में क्या फैच नहीं होता? In the indirect cycle you are fetching the address. Okay, in the indirect cycle what we are doing is, this is your instruction. In this you have the opcode and the address part, and this address part is containing the indirect address. Okay, this is containing the indirect address. So what you need to do is, this instruction will be in the instruction register. You have to read the address from this location. We have the memory in which we have a location 2000. On this location we have an address, and this is the address of the operand. This 3000 address is the address of the operand. So we have to fetch this address. Okay, to fetch this address you will have to run an indirect cycle. Okay, Nivedita? So these are not previous year questions. These are simply these are designed questions. These are not from any examination. These are the expected question of NTA NET. Okay, these are the expected question. Any question can come from these questions. Next question is, a computer uses 1 GB of memory. Suppose the memory is word organized and the size of the word is 64 bits. Okay, then how many address lines are required to connect the memory with the computer? So Devika, Khushbu and everyone, these questions are exactly at the level of NTA NET. NTA NET में इस तरह के questions आएंगे. Okay, this kind of question will come into the NTA NET examination most of the time. Okay, there will be only 1 or 2 questions from every subject that will be hard, that will be complex. Okay, only 1 or 2 questions will be complex, otherwise 90-80% questions will be straightforward on the concept which I taught you. 80% questions will be direct question in NTA NET. You can pick up the previous year questions and you can see only 1 or 2 questions will be complex questions, otherwise all the questions will be they will be easy questions. So we have a main memory, and this main memory is word addressable memory. Okay, this main memory is word addressable memory, and the size of the word is 64 bits, or you can say 8 bytes. So first we will find out the number of words. Number of words in this memory will be 2 to the power 30 bytes divided by 2 to the power 3 bytes. Okay, that means 2 to the power 27 words. There will be 2 to the power 27 words, right? So the address field will be of log base 2 to the power 27, that is 27 bits. Yes, Yakshi, I will provide. सारे बच्चे गलती कर रहे हैं, सारे बच्चे बिल्कुल मतलब सारे के सारे अंधे हुए पड़े हैं, अंधाधुंध बस ऑप्शन लगा रहे हैं, डी, नन ऑफ दीज. अरे ये बिट्स में दिया हुआ है भाई, से पहले बाइट्स में तो कन्वर्ट करोगे ना. यू विल कन्वर्ट दिस इनटू द बाइट्स ना. 64 बिट्स यू विल कन्वर्ट इनटू द बाइट्स, देन यू विल डिवाइड बाय बाइट्स. हाउ कैन यू डू दिस सच अ सिली मिस्टेक? अब तो फिर तुम बोलते हो कि सर वो गुस्सा आ रहा है, तो मैं शांत रहूँ बिल्कुल. इतनी अगर मैं आपसे कहूँ जो जनवरी से तुम लोगों को पढ़ा रहा हूँ, है ना, जनवरी से इतनी मेहनत कर रहा हूँ मैं, बिल्कुल सारा लगा पढ़ा हूँ दिन रात. मेरा खून तुम बढ़ने नहीं दोगे. जब से तुम लोगों को पढ़ा रहा हूँ ना मैं, मेरा वेट घट गया है 5 किलो. सच्ची में तुम मेरा खून बढ़ने नहीं दोगे. So next question is, so we have a instruction of 16 bits. In this 16-bit instruction we have the 10 bits for the address, and we have 2 bits for the addressing mode, and we have 3 bits for the opcode field. Okay, 3 plus 2 5 plus 0 to 10, that is bit number 0 to 10, that is 11 bits for the address, and bit number 11 to 12, that is 2 bits for the addressing modes, and bit number 13 to 15, that is 13 14 15, 3 bits for the opcode. Each instruction is stored in one word of the one memory word. What is the maximum capacity of main memory which can be connected with this CPU? Okay, which can be connected with the CPU. So we have 11-bit address. Okay, we have a 11-bit address, and this is telling you that we can, what is the maximum capacity of main memory which can be connected with the CPU. So we have one instruction in one memory word. This means that memory is word addressable, right? We have memory that is word addressable, and the size of the word is given. The size of the word is 16 bits, because it is saying that we can fix one particular instruction in one word, and we know that the size of one instruction is 16 bits. Okay, so size of the word will also be 16 bits, because we can fix one word, one instruction into one word. And number of words you can find out from the address field. Number of words in the memory is 2 to the power 11. Okay, we have 2 to the power 11 words, and the size of the one word is 2 to the power 2 to the power 1 bytes. 2 bytes, right? That is 16 bits means 2 bytes. So the size of the memory will be in bytes. If you tell me the size of the memory in bytes, it will be 2 to the power 12 bytes. Okay, if you find out this into the words, number of words will be 2 to the power 11. Okay, so the memory is something like this. You have this memory. In this memory you have 11-bit address. 11-bit address means that you have total 2047 words. Okay, total you have 2048 words, and size of one word is 16 bits. Okay, size of one word is 16 bit. So remember, if the memory is word addressable, this means that one address will be given, one particular memory cell will be given one address. Okay. So this question is on addressing modes. This question is saying that we have a pointer int star p equals to address of a, and then we have an increment, and then we have a loop. Okay, so I know that this is used for indirect addressing, right? And then while I plus plus is less than equals to 0, I can match this with auto increment, right? And remaining is loop, but loop cannot be actually indexed. We cannot map this with the indirect addressing. This question is very वाहियात question, बहुत ही गलत question है, because there is no relation between the loops and the index addressing. Okay, index addressing can be used with the arrays only, right? But ज़बरदस्ती आप मैच कर सकते हो. अगर ज़बरदस्ती की बात है तो मुझे पता है कि the pointer is used for the indirect addressing. Okay, pointers are used for indirect addressing mode. So 1 is matching with C, so then 2 is matching with A, 2 is matching with B, so option C is the right answer. Okay, so next question is, there are 64 general purpose registers in a system and instruction size is 16 bits. Okay, we have a 16-bit register, 16-bit instruction, and if there are 10 two address instruction, then how many one address instructions are possible? Okay, so 6-bit address will be there and 4-bit opcode will be there. So you can directly do, if the instruction is of 16 bits, that means that total number of combination possible is 2 to the power 16. Out of these combination, 10 combinations are used for the two address instructions. Okay, in two address instruction you will have two addresses, each address is of 6 bits, right? Then it is asking you, then how many one address instructions are possible. So let us say n one address instructions are possible. With one address instruction you will use one address field, right? So you have to find out the value of n here. The value of n will be equal to 2 to the power 16 minus 10 into 2 to the power 12, okay, divided by 2 to the power 6. Or you can say, you can take the common 2 to the power 12 here. This will become 16 minus 10 divided by 2 to the power 6. Or you can say 2 to the power 6 into 4. Okay, 4 into 2 to the power 6. Okay, so 4 into 6 into 2 to the power 6. That is option A. इसको आप इस तरह से भी कर सकते हो या फिर अपनी पुरानी टेक्निक से भी कर सकते हो. योर पुरानी टेक्निक क्या है आपकी? फाइंड आउट द नंबर ऑफ टू एड्रेस इंस्ट्रक्शंस. नंबर ऑफ टू एड्रेस इंस्ट्रक्शंस विल बी 2 to the power 4, because the opcode field is of 4 bits. Number of 2 address will be 16, that is 2 to the power 4. You have used to 10 addresses, that means remaining are 16 minus 10, that is 6. So 6 into address field, that is 2 to the power 6. यहाँ से भी वही आएगा, यहाँ से भी आएगा. तो ये इक्वेशन आप बना के इस तरह से भी कर सकते हो. इसमें आप 2 एड्रेस, 1 एड्रेस, 0 एड्रेस कोई भी कर सकते हो. So next question is on control unit, and this is saying that number of bits required in the control word for horizontal and vertical microprogramming with the following signal specifications. Right, so we have a horizontal control word, and we know that in the horizontal control word we will use 1 bit for 1 control signal. Okay, and then we have a vertical microprogram control word. You know that in the vertical microprogramming you will encode the signals. Encode means that 10 signals can be encoded with 4 bits, right? With 4 bits you can encode 10 signals. You can encode 33 signals with 6 bits, and you can encode 13 signals with the 4 bits, right? That means in case of vertical microprogramming you will require only 14 bits. Okay, you will require 14 bits for the control signals. In case of horizontal microprogramming you will add all these, right? 33 plus 13 is 46, plus 10 is 56, because 1 bit per control signal. If you have 56 control signals, you will require 56 bits. So the answer will be 56 and 14. Which of the following control unit is the fastest? Okay, which of the following control unit is the fastest? So I told you that hardwired control unit is fastest. Okay, hardwired is the fastest control unit. Then next one is your horizontal, because in the horizontal microprogramming you do not need any decoder, but in vertical microprogramming you will require a decoder. That's why vertical microprogramming is slower than the horizontal microprogramming, right? So fastest control unit is hardwired control unit, that is A, right? Then the next question is on the DMA. A hard disk has the following specification: number of surfaces are 8, number of tracks per surface is 128, number of sectors per track is 128, number of bytes per sector is 512, rotation speed is 3000 rotations per minute. Assume DMA initiation takes 200 millisecond and the bus speed is 8 gigahertz. Then the time taken in microsecond to read 1024 bytes in cycle stealing mode. Okay, this is cycle stealing mode. Is how much? Assume that the bus is 32 bits. Okay, what is the meaning of these two things, 8 gigahertz and 32 bits? This is telling you that we have a data bus. Okay, we have a data bus. Okay, we have a data bus, and the size of this data bus is 32 bits. Okay, the size of the data bus is 32 bits. That means in one cycle, okay, in one cycle you can carry 32 bits into the data bus, and the cycle time you can find out from the frequency. Okay, frequency equals to 1 upon time, or you can say time equals to 1 upon frequency. So time will come out to be 1.1 divided by 8 nanoseconds. Okay, because this is in the gigahertz. So 1 divided by 8 will be 0.125 nanoseconds. That is the cycle time. That means in 0.125 nanoseconds you can transfer 32 bits from the data bus, right? Let me make a diagram, then you will understand how much time it will take, right? So 125 nanosecond means 125 microseconds. Okay, you can multiply by 10 to the power 3. This will become in the microseconds. So because we have to find out the answer in microseconds, that's why I am taking 0.125 microseconds. Okay, that means to transfer 4 bytes from memory to disk, it will take 4 bytes. So it will take 125 microseconds. Okay, DMA initiation takes 200 milliseconds. Okay, 200 milliseconds, and the bus speed is this. I hope you know the diagram. अगर आपको diagram याद है तो फिर ये question बहुत easy है. What is the process of transferring the data from disk to DMA? We know that DMA is used to transfer the data from main memory to disk and disk to main memory, right? We have the system bus. Okay, with this system bus we have connected DMA controller. Okay, we have a DMA controller connected with this system bus, and the DMA controller is connected to disk. Okay, DMA controller is connected to disk, and then this system bus is connected to main memory also. Okay, this is connected to main memory also and CPU also, right? In the question it is given that the data bus of the system bus is having a width of 32 bits. That means you can carry 4 byte into the data bus in one cycle. Okay, and the cycle time we have find out, that is 125 microseconds. That means in 125 microsecond you can transfer from DMA controller to main memory, you can transfer 4 bytes. So there will be 2 times. Okay, first time will be taken to transfer the data from disk to DMA controller. Okay, पहले आप transfer करोगे data disk to DMA controller. When you will have enough data in the DMA controller will interrupt the CPU that I want to transfer this data into the main memory. Okay, whenever DMA controller is having a buffer. Okay, in this DMA controller we have a buffer. In this buffer we will transfer the data from disk to this buffer. Once the data is available in the buffer, DMA controller will interrupt the CPU and will say that hold. Okay, will say hold. Will send a signal that is hold. Hold signal means that DMA controller will request a CPU that please do not use the data bus, because I have to use the data bus to transfer the data from my buffer to main memory. Okay, so CPU will send HLDA signal, that is hold acknowledgement, to DMA controller. Right, it will send the HLDA signal to the DMA controller saying that okay, you can use the data bus. Okay, it will reply with the HLDA signal. Then DMA controller can transfer the data in cycles. That means it can transfer 4 byte, then 4 byte, then 4 byte, like this. So first you need to find out how much time it will take to transfer the data from disk to DMA controller. Okay, how much time it will be required to transfer the data from disk to DMA controller. Okay, let us say this, let's call this time x. Okay, then once you have the data into the DMA controller, you will transfer this data from DMA controller to main memory through the system bus. Okay, through the system bus, and let us say this time taken is y. So you have to find out the time x and you have to find out the time y. Actually time y is already given, and that is 125 microseconds. Okay, this time y is already given, that is 125 microseconds. That means it will take 125 microseconds to transfer the 4 bytes from DMA to main memory. Now we have to find out how much time it will take to transfer 4 bytes from disk to DMA. Okay, how much time it will take to transfer 4 bytes from disk to DMA. Okay, for this everything is given. Okay, for that purpose, to find out that time, in the question everything is given that we have 8 surfaces, number of tracks per surface is 128. All these things are given. Rotations per minute is given, right? So DMA initiation time is given, everything is given in this question. Now we have to find out the how much time it will require to transfer 1024 bytes in cycle stealing mode. Time taken in microsecond to read 1024 bytes in cycle stealing mode. So first we will read 1024 bytes from the disk. Okay, पहले आप 1024 bytes जो है वो हार्ड डिस्क से DMA कंट्रोलर में ट्रांसफ़र करोगे. Okay, how much time it will take? You have to find out the transfer rate. पहले आपको ट्रांसफ़र रेट फाइंड आउट करना होगा डिस्क का ट्रांसफ़र रेट क्या है. एंड वी नो दैट ट्रांसफ़र रेट इज़ नथिंग बट नंबर ऑफ रोटेशंस पर मिनट, दैट इज़ 3000 रोटेशंस पर मिनट इनटू ट्रैक कैपेसिटी. एक ट्रैक की कैपेसिटी क्या है. सो ऑन वन ट्रैक वी हैव 128 सेक्टर्स, ऑन ईच सेक्टर वी हैव 512 बाइट्स. So the capacity of one track is 128 into 512 bytes. Okay, you can transfer this much of data in 1 minute. We can convert this into the seconds. This will become, you can say 50. Okay, 50 into 128 into 512 bytes per second. 50 into 128 into 512 bytes per second. Okay, so transfer time will be size of the data divided by transfer rate. Transfer rate is 50 into 128 into 512 bytes per second. Okay, bytes per second. The answer will come in the seconds. So 512 into 2 is 1024. Okay, this will become 64. So 50 into 64. Okay, 1 divided by these seconds. We can convert this into the microsecond. When we convert this into the microsecond, this will come out to be, we can simply multiply by 10 to the power 3, that is 1000. 1000 divided by 50 into 64. Okay, this will come out to be 20. Okay, 20 divided by 64, that is 10, 32. Again we can convert this into the microseconds. We can multiply by 1000. This will become in the microseconds divided by 32. Okay, so you will get, I think, whatever you will get the microseconds. How many microseconds you will get this? I think you will get 1280 microseconds. Are you sure? 10,000 divided by 32. Ten thousand divided by 32. This will be 312. So what you are saying? Okay, 312.5. This will be 312.5 microseconds. Okay, it will take 312.5 microsecond to transfer 1024 bytes from disk to DMA. Okay, so to transfer 1024 bytes, it will take 312.5 microsecond. Okay, then how much time it will take to transfer 1024 bytes from DMA to main memory? Now we have to see this. Okay, we have to transfer these now these 1024 bytes are available in the buffer. Okay, in the buffer we have 1024 bytes. Now we have to transfer these 1024 bytes into the main memory, and every time we can transfer only 4 bytes because the width of the data bus is only 32 bits. That means at one time we can transfer only 4 bytes. That means how many cycle it will take? It will take divided by 4, that is 256 cycles. Okay, it will take 256 cycles to transfer 1024 bytes from DMA controller to main memory, because in every cycle you can transfer only 4 bytes, right? So total time taken will be 256 into one cycle time is 125 microseconds, right? So how many microseconds it will be? So 256 into 125 will be, I think, something 256 into 125, that will be 32,000 microseconds. Okay, 32,000 microseconds, or you can say 32 milliseconds. This will become 32 milliseconds, right? So it will take 32 milliseconds to transfer 1024 bytes from DMA to main memory. Okay, now we have one more time given, that is DMA initiation time. Okay, and the DMA initiation time is 200 milliseconds. Okay, DMA initiation time is 200 milliseconds. So we have to add this time also. So 200 for DMA initiation. Okay, 200 milliseconds will be taken by CPU for the initiation, plus you can convert this into the millisecond. This will become 0.3125 millisecond to transfer the data from disk to DMA controller, and then transferring the data from DMA controller to main memory, and it will take 32 milliseconds. Okay, 32 milliseconds. So the answer will be 232 point, you can say 3125 milliseconds. Okay, in this question this time is not added, so none of the options are matching, but the real answer will be 232.3125 milliseconds. This will be the real answer. You simply should know the concept. Okay, maybe none of your options are matching. If you know the concept, then the answer is right. Okay, it will take 232 microseconds to transfer this data. Okay, so if we so let's ignore this question. Next question is, zero address instruction is which CPU organization? Okay, so we have studied three type of organization, that is stack organization. For full course, please don't keep the class timing in the morning. Okay, Devika, I will consider this. Khushbu, I will explain memory mapped IO, and you want me to explain memory mapped IO and IO mapped IO. Okay. Okay, what is the CPU cycle stealing mode? So cycle stealing concept is very good concept, and it is a very it is a very interesting concept. Let us understand this. Padam is saying that what is the cycle stealing mode? So DMA runs in three kind of. So what is the DMA? DMA is direct memory access. Okay, DMA means direct memory access. Okay, so DMA is a very useful technique to transfer the data from input output devices to main memory, specifically if we say from disk to main memory. Okay, we know that we have this system bus, and from this system bus all the input output devices, memory and CPU are connected. Okay, all the input output devices, CPU and the main memory are connected to this system bus. Okay, the question is, if you want to transfer the data from input output devices to main memory, then how we should transfer this data from input output devices to main memory? Should we involve CPU or not? The question is because the main functionality of CPU is to execute a program. Okay, to execute a program, right? And if you are involving CPU to transfer the data from IO to main memory, then it will be a very wastage of the time. Okay, it will be the wastage of time for CPU. Okay, there are three modes of transfer that are called as modes of transfer. Modes of IO transfer. Modes of IO transfer means if you want to transfer the data from IO devices to main memory or main memory to input output device, we are concerned about transferring the data from main memory to IO and IO to main memory. Okay, or you can say you want to transfer the data from disk to main memory and main memory to hard disk. For that we can use three techniques. Okay, let me tell you what are those three techniques. Those three techniques are called as programmed IO. Okay, programmed IO. Second is called as interrupt driven IO, because before understanding the DMA you have to understand what is the meaning of why we are using the DMA. Okay, interrupt driven IO. And third one is DMA. Okay, so let us assume the situation. Okay, so let us say let's take someone, Khushbu. Okay, so let's say Khushbu gets married after 1 year. Okay, after qualifying JRF, and she will get the admission in IIT, and then she will get married. Let us say Khushbu gets married after 1 year, and let us say Khushbu does not know how to make the rotis. Okay, how to make the chapatis, Khushbu does not know. Okay, there are three ways in which she can learn how to make the chapatis, right? First one is, let us say if Khushbu, so let us say we have Sasu Ma of Khushbu, right? We have a Sasu Ma of Khushbu, and the Sasu Ma is master. Okay, master of the house is Sasu Ma. As the CPU is the master of the CPU, Sasu Ma of Khushbu is the master of the house, right? Now the Sasu Ma says that Khushbu, please make the 10 rotis. Okay, please make 10 rotis. So there are three ways. Let us say if Khushbu does not know how to make the rotis, then her Sasu Ma will stand behind her and will instruct how to make the rotis, right? But in this situation what will happen is her Sasu Ma's the time will be wasted, right? उसकी सासू माँ का जो टाइम होगा वो वेस्ट होएगा, क्योंकि वो उसको खड़ी होकर सिखा रही होगी रोटी बनाना, राइट? पीछे से लग रहे होंगे और सिखा रही होगी, राइट? दूसरा तरीका क्या है कि आयो, सेकेंड मेथड इज लेट अस से खुशबू नोज हाउ टू मेक द रोटीज, बट खुशबू नोज ओनली हाउ टू मेक ओनली वन रोटी. So after making one roti, Khushbu will interrupt her Sasuma and will say that I have made a roti. Then her mother will come and will check the roti and will instruct that make another roti. Okay, then she will make other roti, then will interrupt her mother that I have made a roti. Right, like this Khushbu will, now the Sasuma is not standing behind the Khushbu. She is just like she is sitting behind and she is watching the serial, and Khushbu is making the roti. Khushbu is simply telling her Sasuma that I have made a roti. Every time she is making a roti, she is interrupting her but still she is interrupting, right? Still the time is wasted of her mother, because she is interrupting her. So in both of the scenarios, in the program driven IO and interrupt driven IO, is Sasuma is involved in making the rotis. But in case of DMA, Sasuma will not be involved in making the rotis. Now Khushbu is very master. Okay, Khushbu is the master now, right? Like that, CPU, for example, if let us say CPU instruct the IO that please transfer some bytes from device to memory, then CPU will tell how you need to transfer the data. Okay, how do you need to transfer the data? Then CPU will instruct the IO. Okay, CPU will say that first load the data from this location. Okay, then store this data at this location. Okay, store this data at this location. That means in the program driven IO, CPU will execute a program to transfer the data from input output devices to main memory, or main memory to input output devices. That means when you are transferring the data from IO to memory, CPU is involved. Okay, CPU is not able to do anything else. CPU will not be able to execute any instruction, because CPU is involved in transferring the data from IO to memory, memory to IO. Second situation is interrupt driven IO. In case of interrupt driven IO, whenever data is available in the input output buffer will interrupt the CPU that I have some data and I want to transfer this data to memory. CPU will say okay, transfer the data. Then IO will transfer the data to the main memory. In this case, CPU is not involved in transferring the data, but still it is involved, because whenever input output device will interrupt the CPU, okay, whenever input output device will interrupt the CPU, then CPU will have to do some work, right? CPU will have to acknowledge the input output devices. But in case of DMA, whenever you want to transfer the data from disk to main memory, you do not need to tell CPU. Okay, you will simply request the CPU that I want to take the hold of the bus. IO device, or you can say DMA, will request the CPU for holding the data bus, and CPU will reply with the HLDA signal that you can use the data bus, राइट जिस तरह से ऐसा मान लो कि DMA ऐसा है कि बस इस केस में खुशबू जो है वो अपनी मदर को बस इंटरप्ट करेगी कि मदर मुझे किचन यूज़ करना है, उसकी मदर कहेगी ओके यूज़ कर लो, बस इतना कम्युनिकेशन होगा उसकी मदर के और खुशबू के बीच में, राइट। इस केस में इंटरप्ट ड्रिवन आईओ में खुशबू और उसकी जो सासू माँ हैं उन दोनों के बीच में उसमें थोड़ा सा कम्युनिकेशन रहेगा। वो अब खुशबू क्या करेगी, एक रोटी बनाने के बाद में वो अपनी माँ से चेक कराएगी, हर एक रोटी बनाने के बाद में अपनी मम्मी से चेक कराएगी। प्रोग्राम्ड आईओ में जो मम्मी है वो पीछे ही खड़ी हुई है, वही सिखा रही है बनाना। तो यू विल सी दैट मोस्ट ऑफ सो CPU टाइम विल बी वेस्टेड मोस्ट ऑफ द टाइम इन दिस, okay, CPU time will be wasted in programmed IO. In case of interrupt driven IO, the CPU time will not be wasted too much, but it is still involved, right? CPU is still involved and some time will be wasted. But in case of DMA, very less time of CPU will be involved in transferring the data. Now what is the meaning of cycle stealing mode? Cycle stealing mode means that, so I told you that we have the system bus, okay, and the system bus is connected to the DMA controller. DMA controller is having a data bus and the address bus, okay. So DMA controller is connected to system bus, and then the disk is connected to DMA controller, right? And here we have the CPU is also connected to system bus, because we have the common shared bus, okay. We have the common shared bus between the CPU, main memory and IO. We have a common shared bus. What is the meaning of cycle stealing mode? We know that when CPU is executing, so CPU will fetch instruction and will execute instruction, right? अगर CPU कोई भी instruction fetch करना है, CPU का काम क्या है? The work of CPU is to fetch instruction and execute instruction. That is the main functionality of CPU, right? CPU will fetch the instruction from the memory and will execute the instruction. What is the functionality of DMA? The functionality of DMA is to transfer the data from disk to DMA controller, then DMA controller to main memory, right? You will see here the fight is only about the system bus. System bus की fight है, कौन system bus लेगा, CPU system bus को use करेगा या फिर DMA system bus को use करेगा। अब CPU तो मास्टर है पूरे कंप्यूटर सिस्टम का, राइट? अगर DMA को सिस्टम बस यूज़ करनी है तो वो CPU से बिल्कुल पहले रिक्वेस्ट करेगा, बट समटाइम्स नाउ इट विल वर्क एज ए थीफ, okay. Now it can steal the system bus from the CPU without asking from the CPU. It can use the system bus. How? For example, when CPU is fetching the instruction, okay, when CPU is fetching the instruction from memory, that means CPU is using the system bus, right? CPU will use the system bus only when it is fetching the instruction from memory, right? But when CPU is executing instruction, CPU will not require the system bus. When CPU is executing a instruction, CPU will use the ALU and control unit and will not require the access to the system bus. So at this particular moment of time, DMA can use the system bus. DMA will steal the cycle and will transfer the data from DMA controller to main memory. Tell me whether you understood this or not. Okay, you understood this concept or not? CPU will use the system bus to fetch the instruction and DMA will use the system bus to transfer the data from this to main memory, right? So whenever system bus is free, DMA will steal the cycle and will use the system bus. And when system bus will be free, CPU will not use the system bus when it is executing the instruction. CPU will use the system bus when it is fetching a instruction, right? So when CPU is not using the system bus, or you can say CPU is executing a instruction, then DMA can use the system bus. This is a very beautiful concept if you can understand this, right? So that is called a system cycle stealing mode. Then we have one more mode that is called as burst mode. So in the burst mode, let us say if you want to transfer 5 megabyte of data from disk to main memory, then you will transfer all data in one shot. Okay, you will transfer the whole data in one shot in the burst mode. Okay, then we have block mode. Block mode means that you will transfer only one block of the disk at one time. Let us say we have the block size of the disk is 5 kilobyte. Okay, and you have to transfer the burst, you have to transfer the 5 megabyte of data, right? So you can transfer only 5 kilobyte in one cycle. This is called as one block mode. Okay, block mode means you can transfer one block at one time only. Okay. So the next question is, so there are three modes of DMA, that is bulk mode, or you can say burst mode, block mode, and cycle stealing mode. So I will teach this in the details in the complete course. I skip this in the crash course because this is not that much important for NTA NET, and but we will study this in the complete course in the details. Oh my god, 8:15. ओके, तो टाइम अभी और हो गया है ना? So let us meet in the next class. We will continue. So I am giving you this PDF. Try to solve these questions by yourself. In the next class at 9. So we will start the next class at 9:30 p.m. Okay, from 9:30 p.m. to 11:30 p.m. We will have the first class of the microprocessor. Okay, we will have the first class of microprocessor. So in this class I will cover the 8085 microprocessor. Then in tomorrow's class I will cover 8086, and the last class I will cover the previous year questions of microprocessors. So in the next 2-3 classes we will complete computer architecture and microprocessor also. Okay, so today is the first class of microprocessor. Please do not forget to attend the class. There are some beautiful questions in this PPT and please try to solve these questions. Okay, Khushbu, your doubt, conflict, capacity and compulsory miss. Because of this like time is not we are short of the time. So Khushbu, in the next class, before starting the class, I will discuss your doubt. Okay, so first I will explain the capacity, conflict and compulsory misses. Then I will start the next class. Okay, thank you everyone. Let's meet at 9:30 p.m.